In free fall, the form of the equations for velocity and displacement don't change. We just use delta y for the vertical displacement, as y is the direction of the vertical axis on a graph. So instead of having x, which is what we've been using, we're going to use y. It just means you're going up and down. And we'll replace acceleration with negative g, which is negative 10 meters per second squared. So here's our vertical velocity. All right, we've got vf, vi, and at. And here's our vertical displacement, in other words, the height or how much the object has fallen. We then substitute in a is equal to minus 10. So vf is vi minus 10t. Delta y, no change there because you don't have the acceleration. But for our equation here, we replace 1/2 t, right? See this right over here? 1/2 of a negative 10 is negative 5. And t squared, of course, just stays the same. Remember that slide that started this section where it had the gentleman dropping a ball and there was a flash camera taking pictures of it every second? Here's the analysis of it. We'll start on the left side here. The acceleration is minus 10 meters per second squared. The velocity here keeps increasing in the negative direction, and this gives us a displacement. The velocity increases as a linear function of time, the displacement as the square of time. So the ball is dropped up here. Okay, after 1 second, it falls, looks like 5 meters here or 5 feet, whatever we were measuring. After 2 seconds, here, 3 seconds, what do you notice about the displacement? Right, it's increasing quite a bit with each second. And then over here, for the last at 5 seconds. The velocity also is increasing at every point, but not as fast, because that's only a function of t. Displacement increases as t squared. Velocity increases as a function of t.